Hello and welcome everyone to another Applied Flow Technology webinar. My name is Nick Vastine. I'm a business applications engineer here with AFT. And today's webinar, we're going to be covering our latest product or our newest release, which is the AFT Arrow Extended Time Simulation module. So this is the first time that we're bringing transient capabilities to AFT Arrow. More recently, earlier last year, we released AFT xStream, which was our first foray into compressible transient analysis for gas and steam systems. And so now we're building on that experience and looking at extended time simulation in AFT Arrow. A lot of what we're going to talk about today is pretty introductory. So if you've never used an XTS module or any of our other AFT products that use transient analysis, so AFT Fathom, AFT Impulse, or even AFT xStream, we're really starting from bare bones here. We'll take a look at some of the differences towards the end of the webinar, and then we'll go through the process of how you can start from your base steady state model and build transient analysis on top of it. So before we get too far into it, let's look at our agenda for the day. So we have a few different topics that we're going to cover. Again, this is an introduction, so we'll start with what is Arrow XTS. So XTS, again, standing for the Extended Time Simulation. We can just think of it as transient analysis within AFT Arrow. How does that transient analysis module work? And then who is it for and what can you use it for? So we'll look at quite a few different typical applications, one of which we'll cover in an example. So we'll look at filling an intermediate tank, and we'll look at how you can specify a pressure safety valve and determine kind of the event timing if there were an overpressure event. From that, we'll kind of generalize transient analysis and AFT software. So today we're doing an introduction to XTS, which is one approach to doing transient modeling. We also offer the method of characteristics, which enables us to track pressure waves and kind of pressure swings from things like closing valves or startup or shutdown of compressors or pumps and things like that. And so the two different approaches have two very different intentions, but in general, what we're going to learn today, we can apply a lot of those same skills regardless of the back-end transient solver. So as we generalize that transient analysis, as I mentioned, we also offer a product called AFT xStream, which does compressible gas and steam system transient analysis for much more rapid transients. So if you have a relief valve opening and you want to see the sudden drop in pressure at that point permeate through your system, or if you're rapidly starting up a compressor and you see a quick change in speed, those things are going to be relegated to AFT xStream, where Arrow XTS is good for a lot of other applications, just not those really rapid transients. So we'll bring it all together at the end, again, taking what we learned today, how we can try to generalize it to a lot of different transient applications, and then hopefully having a better understanding if you are looking at compressible flow systems, which hopefully you are if you're here, which tool is going to be the right one for you as you're doing transient analysis. So as an introduction, we'll take a look at one, what is the XTS module? How does it work? And then finally, who is the XTS module for? So as I mentioned, XTS stands for Extended Time Simulation, and it's an add-on module that's going on top of the base program. So if you own AFT Fathom, or if you own AFT Arrow, you can purchase the XTS module to unlock these specific transient capabilities. So when we go into our example, we'll take a look at how you might have your existing steady state system and all of your different scenarios for steady state analysis. We can then turn on the module, unlock these transient capabilities, and do sort of a different type of analysis. So again, it's built on top of those base products and those base solvers. How does it work? So the XTS module uses a series of steady state snapshots. You'll hear me use that phrase a lot. So it's important to understand what that means. And so the series of steady state snapshots is modeling different events through time by breaking up your system into what it sounds like a series of steady state snapshots. So you'll have a steady state at your initial condition. That first time step will then inform your next time step. So if we have, for example, accumulating mass in a tank, let's say we're doing a tank filling, In the first time step, we're going to pump a lot of mass into that tank. That's going to reduce our driving force for subsequent scenarios or subsequent time steps. Then we can do another steady state snapshot, determine the new mass flow. That'll tell us how much more mass accumulates, so on and so forth. And we can keep track of those changes over time. So this is why we can build a transient solver on top of two steady state tools. Typically, AFT Fathom is incompressible steady state and AFT Arrow is compressible steady state. We can use those two steady state solvers to track these changes over time. Again, with the core assumption that with any small change to your system as your tank gradually fills, or if you're gradually changing the speed of a pump or of a compressor, that it's going to immediately reach that new steady state. So who's the XTS module for? Because it's an add-on module on top of these base products, you can apply it to any existing Arrow model and by extension, any existing Fathom model. And you can apply the XTS module to start your transient analysis. So it's not necessarily a replacement to that steady state analysis. Again, I imagine the majority of your systems are going to be operating at steady state, especially if you're in process. And so starting from that steady state basis where you're going to do the majority of your work, then you can turn on the module, access those transient capabilities, and then perform your transient analysis. So it's going to be useful for all sorts of different things. Again, one that I've already mentioned is seeing how you can accumulate mass in a tank, where very gradual changes in the mass downstream or upstream aren't going to create significant pressure waves that, in this case, the XTS module will not track. Because it's assuming that at each time step it's reaching a new steady state, it's unable to track things like pressure waves that would transmit through a system, for example, in a water hammer event or in a relief valve event, or any of those what we call rapid transients. Don't worry about that too much up front. Again, we're going to start kind of foundationally, and then towards the back end of the webinar, we'll look at how do we distinguish what would be better modeled as a quote-unquote slow transient or a quote-unquote rapid transient. So accumulating mass in a tank, that's the example that we're going to look at today. In the case of compressible flow, we'll look at what we typically call a blowdown. We're starting from a charged tank, we open a valve, and then we blow down the tank and drain it. Or a charging of a tank, which is what we'll look at today, where we're charging an intermediate vessel. We can determine things like process timing. How long does it take to blow down a tank to a certain amount, or how long does it take to charge it? If a relief valve is going to open or close, is that within an acceptable range for our timing? Things like that. We can also look at speed changes. So an event like a pump startup might be pretty violent and might create a lot of pressure waves. That might be better for something like AFT Impulse or AFT Extreme. But if you have very gradual changes in compressor or fan speed, or if you have kind of step changes where for a part of the day this compressor is running and for another part of the day it's not, over years and years, how does that impact your operation? That would be something we would call a slow transient, whereas the actual ramp up of the compressor might not be captured as acutely in XTS as it might in something like AFT Extreme. Along those same lines, we can look at something like valve position changes, where if we slam a valve closed, because we're looking at a series of steady state snapshots, what the XTS module might look like is the valve will be fully open, and then in the next scenario, the valve will be fully closed. That means that you're getting full flow, and then in the next time step, you're getting no flow. It won't capture the pressure rise from the valve reaching that closed state or the sudden change in flow rate, or if you're familiar with water hammer analysis, things like the water hammer sequence. Again, it's making the assumption that between any change for any of our time steps, it's immediately reaching that new steady state. So if you're changing your valve very gradually, where it has time to dissipate those pressure changes, then the XTS module would be more than suitable to try to capture that transient event. We can look at relief valve sequencing, where again, we won't model the relief valve opening and the sudden drop in pressure, but it will tell us, at what time is this pressure exceeded, which of these relief valves would be triggered first. And we can do the same thing with control valves, where if a control valve fails in the sense that it's unable to meet its set point, we can see that as a result of whatever transient event that we're specifying for the system. One final thing that I will touch on, which is kind of a unorthodox application of the XTS module, is we can use it to replace an iterative sweep. So we can sweep different parameters. Let's say we wanted to look at the full range of a control valve open percent to see, at 5% increments, what is our flow rate going to respond? We could specify that in the XTS module because all it's going to do is at 5% open, 10% open, 15% open, it'll run each of those steady state time steps, which can save us the effort of creating a large scenario tree and doing our analysis in that way. So this is something that you can think about. Again, as we start looking in the software, it'll probably make a lot more sense and not something that we're going to cover in detail through the rest of the webinar. But if you have any curiosity, if you want to see an example of that, feel free to reach out to us and we can see what we can prepare. So these are some typical applications that I've thought of or our team has thought of, but of course it's not comprehensive. We can really model anything that falls within these core assumptions. The first is that heat transfer is not available in Arrow XTS. Of course, heat transfer is very important in compressible flow because as you add heat into or out of the system, if it's exchanging with the surroundings, that's going to impact, one, the density of your fluid, that'll impact the velocity and the pressure loss, how that'll distribute through your system. So heat transfer is important, but when you are doing transient analysis, the heat transfer implications of transferring through different time steps or tracking that over time is much more difficult. And because of that, one of the assumptions that we've applied to Arrow XTS is that it's adiabatic. In a lot of cases, this may be reasonable. You may have your pipes all be insulated, and this should be a good first pass for the majority of your analysis. Again, by default, a lot of our pipes are specified as adiabatic as you're drawing your model in Arrow. So just something to be aware of. As long as it fits that condition and you're okay with that assumption, then you're okay to move forward with your transient analysis in Arrow XTS. One of the differences I'll touch on towards the end of the webinar is how AFT xStream will capture those heat transfer implications. And so if that is a major concern, then we do have an alternative tool that can capture that heat transfer capabilities. The next one is something that we've touched on pretty frequently, is that because we're modeling the transient analysis as a series of steady state snapshots, anytime that you see a change over time, it's going to immediately reach a new steady state. So if we take our valve and we go from 100% open to 100% closed, if we do that in a single time step, then we have to be okay that it's immediately approaching that new steady state. You're not going to see the reflection of pressure waves that you might in a more complex tool like AFT Impulse or AFT xStream. Again, this assumption will be okay for a lot of different applications. Again, a lot of the applications that we've listed here on the left. And again, towards the end of the webinar, we'll touch on the differences between what we call a slow transient and a rapid transient. So most important, we're not considering the transition between those time steps. We consider it in the sense that we can keep track of things like tanks filling or the positions of valves or accumulation in that sense. But we aren't trying to capture things like pressure waves or advective transmission where things are going to travel along the fluid as it moves with the system. So for example, if you were pumping in a hot fluid and then you had a step change and you're pumping in a cold fluid, that's what I would call advective transmission, where those parameters are going to follow at the velocity of the flow rate. So it's not capturing that. Again, it's taking the steady state solver present in Arrow and in Fathom and applying that for transient analysis. So those are the two big assumptions. Try to keep those in the back of your mind as we start taking a look at our example. So the example that we're going to look at today is an intermediate tank filling with a pressure safety valve. Today we will take a look at how you might specify a pressure safety valve, and we might go through the steps of defining it, but ultimately we'll use it as an example of event logic and automatic reactions from some of the junctions that we have built into our tools. So here in our case, we have a 1-inch line that's consistent across the entire piping system. We have a very small orifice. What that's going to do is create back pressure so that when we open this valve and we allow this tank to see this huge high pressure, it's not going to flow all the way through. It'll create back pressure and will gradually fill this tank to approach this upstream pressure. The goal of our analysis is to determine the time that it takes for our tank to reach 350 psi. So here we're at essentially atmospheric, and here we're at 375. So we want to know how long it takes to reach this new pressure. Again, this is an example of charging a tank. You can imagine much more complex systems. You can have all of these other different criteria that you might want to model in your different scenarios. Here we're going to define a few things. So we're going to look at the transient control of the model. We'll see what that looks like in software. That includes the duration of the transient, which is just how long the event is going to run for. The time step, where the time step is essentially the resolution that we're getting. So if we think about a 1-minute simulation, if we had a 10-second time step, that means we're running the first steady state for 10 seconds. We're letting whatever mass accumulate for those first 10 seconds. Then 10 seconds later, we're running a new steady state. That informs the next 10 seconds, the next 10 seconds after that, so on and so forth. So one of the things that you can control with the XTS module is how finely your resolution is for this modeling. Obviously, the smaller time step, the more accurate your results are going to be because it's tracking that information more tightly. But that's going to come at the expense that you're going to run more and more different scenarios, right? So every time that you have a new time step, you're rerunning the model, especially if you have a very large system that might run into problems during your steady state problems or your steady state analysis. Then a superfine time step might create issues, especially when you have hundreds of simulations that you're trying to run across your transient. So something that you'll consider, especially if you start experimenting with the XTS module, if you start doing this analysis yourself, you can make this finer or coarser. And as a result, that'll impact both your runtime and ultimately the accuracy of your results. So as an engineer, it's your responsibility to take a look at that. What is reasonable? How do you balance those two variables? So no matter what scenario that you're modeling, you're always going to specify the transient duration and the time step. Specific to our model, we're going to specify a junction transient. So we want to specify how this valve opens over time. And we want to open it in such a way that we're minimizing its effect on time to fill. If this valve opens over 20 seconds and we're trying to figure out how long this tank fills, that might be more representative of your system. In our case, we just want to see if this were to open instantaneously within one time step, where again, it's going from fully closed to fully open, how does that impact our fill time? That should be the shortest possible fill time we can look at. Finally, we're going to specify the dimensions and the thermodynamics of the finite tank, which again is introduced by turning on this XTS module. Because in steady state, no matter what, in steady state, we're not going to see an accumulation in this tank. Whatever comes in should come out. And depending on how we model it, which we'll take a look at in the software, we will either meet that assumption or we won't. So these are the things that we have to define in addition to our typical steady state definition and our typical steady state analysis. And then after we do that, we'll consider how we would specify a pressure safety valve in case we have an overpressure event. So building on our intermediate tank filling scenario to now what if we have this relief valve and we overpressurize it, when would our relief valve open, for example? So hopefully that's a pretty good introduction. Hopefully we're all still tracking with what I'm talking about. And now we can jump into the software. So here we have AFT Arrow 9, where Arrow XTS was introduced with this version of the software. So if you are currently using AFT Arrow 8 or even AFT Arrow 7, you'll have to upgrade to access this new module. Here we have our steady state scenarios. So I have a steady state case with no flow, where I've just closed this valve. I've manually defined this tank as 0 psig, which is atmospheric. And if we run our model, which I already have output for, we can see that we don't get any flow. It makes sense. Our valve is closed. We have no driving force. Well, we have driving force, but it's closed off by this valve. And so it's consistent with our expectations. We can also consider if the tank is full. The way that we recommend doing that is by using a branch junction. So what the branch junction assumes is that any mass flow coming in is going to equal the mass flow coming out. And it's also going to assume that the pressure out at this pipe is equal to the pressure in at this pipe. So if the tank is full, you're not going to have any accumulation at steady state. And that means that this is our full tank condition, where in this case, we can see that we do have a mass flow, which will be our final mass flow when we start looking at our transient analysis. So what we're going to look at is the transition between this no flow case, where the valve is closed. If we start filling this tank and we get a full tank, how do we transition between those two, and how long does it take for our tank to reach that 300 psi criteria that we've set? So again, anyone can start from a typical steady state Arrow model, and then we can add on our transient capabilities on top. In the lower right, we can see this button called Add-on Modules. If we click that, that'll take us to the new analysis setup window, which is new to AFT Arrow 9 and that kind of suite of applications, including Fathom 12, Impulse 9, xStream 1 and 2. And here we can check the box to activate XTS. We can see by activating the module, we need some new input. So it's flagging us with this exclamation point. And if we go to this transient control window, we can see the simulation duration. This is the total amount of time that we're going to run the simulation for. So here we're going to run it for 15 seconds, but we can also get pretty long in terms of our extended time simulation. So if you instead need to look at the course of minutes or the course of hours or even on the course of years, I don't think I've ever seen a model that is running for more than a couple hours, but we can consider that. If you do have that system, you're looking at a 25-year horizon. How long is this compressor going to take to build its tank? I don't know who's answering those questions, but we can answer that for you. In our case, we'll stick to seconds, and here's where we can set the resolution of our transient analysis. So by default, our time step is going to be 1 second. If I want to get a finer resolution, we can make it half a second. And we can see that now we have to run 30 total time steps. That's the equivalent to us making 30 different scenarios and running them one after the other, where we can keep track of how things change, like how all of the mass is going to accumulate in our tank. So we're also going to save the output to file every time step. This is generally a good idea because it's going to make some of the other features that we'll look at much easier. So I would leave this the same by default. So just to reinforce the concept of the time step controlling resolution, again, if I were to make this 0.1 seconds, it's going to run a new steady state every 0.1 seconds. That's going to give us a pretty accurate measure of how much mass accumulates in our tank, but it's going to run for 5 times as many as our half-second time step. So you're always going to be making that trade-off. Again, it's best to experiment, and kind of the spirit of AFT software is make a scenario. You can explore these different variables without losing, all of your work or losing control over what you've been working on. So we've defined our simulation duration. Again, if we think back to our example, we've defined our transient control. We have a 15-second simulation, and our time step is half a second. So let's hit OK. And here we're going to clone without children, and we'll call this our transient tank filling. And let's actually do this from the no flow case. And what that'll do is that'll also bring over the tank that we have specified. So now what we can see in the tank with the XTS module enabled, we have quite a few more options. Here, rather than an infinite tank, which will act as an infinite source or as an infinite sink, we can say that it's a finite tank. In our case, it's 100 gallons in size. And we're going to be operating at ambient pressure, which is what we're going to call our empty tank. We can also calculate what those initial conditions would be. Again, if you have a much more complex system, this might be useful. Like if you have a gas accumulator kind of protecting a compressor, like a bladder or something like that. And then we can also pick our thermodynamic process. So we have adiabatic by default. We can also have isothermal. So if it's over really long time spans and the tank is able to heat exchange effectively with its surroundings. It might stay fixed at the surroundings temperature. That might be an okay assumption. We can also specify a known heat and volume versus time. And so when I hit this button, you can see in the transient tab, which we'll take a look at in the valve, you can specify the time, how much heat is added, and if the volume is changing at all. In our case, to keep things simple, we're just going to stick with adiabatic. We know our initial conditions because we know it's at atmospheric, and we're saying that it's 100 degrees Fahrenheit. So we can hit OK. Here we have our valve on the left. Also make sure that we have transient turned on. So here in this valve, we have to specify our valve transient. So again, if we're thinking about steady states, the ideal case that we want is this pressure to feed to this atmospheric as quickly as possible. But that's not a true steady state that we can achieve unless we have this valve here that's closed, and then we can suddenly open it, and that's what allows us to have this driving force, allows us to keep this tank empty. So within our valve, we have the normal specifications that we would have had from our other scenarios or from our steady state cases. Here we have 1000 CV, so I'm trying to minimize the losses seen through the valve. And here we have our transient defined. So when you're defining transients and doing transient analysis, this is kind of how you poke the system or how you initiate the transient event that you're trying to analyze. And so you'll see this transient tab on a lot of different junctions. So we saw it in the tank junction if we have our known heat and volume versus time. You can also see it in things like compressors. So here in our compressor, we can specify a speed transient. So if we wanted to do a gradual ramp up over time, if we use a controlled compressor, we can also change the set point. So here we have a volumetric flow rate control. We can change what that volumetric flow rate is. The same thing with discharge pressure or suction pressure. We have full control over how that is changing over time. We can also look at things like the control valve, where again, it's going to have a transient control where you can set what is the control pressure of this valve over time. So it allows you to, again, take your existing model if you have all of your compressors and all their control valves next to them. If you have these valves distributed and you're trying to model a steam blowdown where you're shutting all these isolation valves, again, you get a lot of the same flexibility that you're accustomed to using AFT software. Some other junctions might have built-in logic. So in the control valve case, and what we'll look at in the valve, is we are specifying how this transient changes over time, but we also have cases where the junction itself will just react to changes. So the check valve, sort of like how a check valve will close if in a steady state run, it determines the check valve needs to close. It can determine if there's reverse flow, shut it, and then maintain that going through different scenarios or going through the different time steps as you step through your transient. And similarly with the relief valve, you can specify things like your set pressure and your blowdown pressure so that it can exist between those things instead of just being in a state of open or closed. So again, just think about it as a series of steady state snapshots. Any of the things that you're accustomed to in steady state, you can do here. And now we can specify those additional transients to kind of guide the system through time, which is ultimately what we'd be interested in doing our transient analysis. Here, what I have specified already is a valve opening. So in optional, I have marked the special condition as closed. That's saying that for our very first time step, the valve is closed. And that matches here. So in our very first time step at time equals 0, the valve is still closed. And then we can open it in half a second to 1000. And then we'll maintain that throughout the entire transient. We can look at a graph and we can see that it makes that pretty rapid step change over our half-second time step. If we were to change our time step to 0.1 seconds, like one of the options we looked at, we would instead see the valve gradually open and then hold that full open. So there are other options that we won't get into here that can more accurately capture how a valve opens. Obviously, a linear change in CV is not very common. A glow valve is going to open very differently from a ball valve or from a gate valve. And so all of that can be captured within the software where you can see how the CV will change with open percent and then you can specify this in open percent as well. So you can say go from 0 to 100% open, and it can make those CV considerations for you. Here we'll leave it as we specified, and then we'll clear out our specifications. And I believe we should have everything that we need to run, but before we run, we will go back to the presentation and we'll take a look at kind of an approach for how you perform a transient analysis. So it'll reflect a few of the things that we've already talked about, but just kind of formalize a process, which I usually prefer trying to follow a series of steps than just taking it all in at the same time. So how do we perform a transient analysis? This is something you can take not only for Arrow XTS, but for Fathom XTS and Pulse xStream. Again, creating kind of a framework across all of these different applications. First, I would calibrate or confirm your system in steady state. So you're applying a lot of changes by creating an analysis in the transient domain or over time. So it's important to make sure that your system's calibrated, that steady state is all figured out. So that way, when you start your transient analysis, you're starting from a good place. In our case, I've made up our example, so it's perfectly fine. Everything is good. You can determine what transient event you're modeling. So in our case, we want to model the valve opening that's going to allow our immediate tank to fill. We want to anticipate what response we're going to expect, and then that's going to be useful once we start looking at our results. So it's important not to just look at the software and face value, whatever output it's putting out. It's always important to think, is this realistic? Is this consistent with what I think the system should do? And from that, that'll give you a good, engineering basis as you start doing your analysis. Is the software, accurate and responsible? Do I need to shorten the time step? Would that give me better results? Things like that. So in our case, because we're filling a tank, we're going to look at the tank and it should fill asymptotically to the inlet pressure. So as the tank accumulates more and more mass, it's going to accumulate more and more pressure as well. That's going to decrease the driving force, so we're going to see less and less mass flow going to that tank. So those are the two expectations that we have, and those are the two expectations that we're going to try to confirm within the software, and then they'll do the actual number crunching, so it can give me a specific time to fill it, and not necessarily just the trend that I should be expecting. Once we've calibrated our system and we know what kind of event we're trying to model and how that event is going to react in our system, we can define the transient specifications. So these are the steps that we've already taken in our model. In our case, we have a 15-second simulation with a half-second time step, and we're going to look at an instant valve opening. Instant in this case, I'm just saying that the valve is closed in one time step, and in the very next time step, it's fully open. We're not trying to consider how the valve gradually opens or gradually closes. I just want a binary change from closed to open. Finally, we can perform the analysis, and in our case, we're trying to answer the question, what is our time to fill our tank to 350 psi? So try to keep that number in mind. It should hopefully be less than 15 seconds. If not, doesn't seem like a very well-prepared webinar, I would guess. So we can run the model now. Everything's all defined. We've defined our transient duration. Everything's gone okay. Let's see. Let's try reloading the scenario and if it'll run. There it goes. So here we have our solution progress window. Again, you should be accustomed to this if you've used AFT Arrow before. Now it's a little bit different because we can track the transient over time, so we can see how it's gradually filling as it runs through those 30 different time steps that we've assigned to it. Here we can see that flow rate relaxation is being lowered for every scenario, or for every time step, I should say, rather. Where again, that's one of the caveats that I mentioned. If you have a very complex system and you're trying to push that into transient analysis, because all it's doing is running a steady state simulation of your model over and over, it can run into those same challenges over and over. So that's why it's good to make sure that your steady state model is running well and running effectively, instead of just jumping directly into a transient analysis where the runtime is going to be significantly more. So our steady state runs, each of those were maybe 5 seconds at most. And now that we're running 30 of them, obviously your runtime is going to be more significant. Here we can do the same graph results, visual report, and output. We'll jump into the output tab. And here we can see that our output looks a little different from normal as well. So it looks like, let's see, we ran into an issue with our licensing, but let me pull up another model that I have, which we should be able to run as well. So here we have the same simulation. This is why it's always good to come prepared with a backup model. Where here we have our transient tank filling. We've done the same specifications. We still have our tank with 100 gallons in volume. And now if we take a look at our output, we can see some differences. So here we can see at the bottom a timeline where this will step through all of our different time simulations. So if we step through time, we can see at time step 0, we have 0 mass flow because our valve is closed. That's matching our expectation of this no flow case. And as we gradually fill the tank, we see the most mass flow in the first time step at 2.6 pounds per second and very little flow coming out of the tank. And as we go further through time, we can see how this mass flow rate gradually decreases. And if we jump to 5 seconds, we can see that it's continuing to drop. We can also use this new transient tab in our output, and we can see that over time, we can look at each junction. So here we'll look at the tank, where we can see at time 0, half a second, 1 second, 1.5 seconds, all the way down. We can look at the pressure inlet. So here we can see that we start at our 14.7, our atmospheric condition, and as we accumulate more and more mass, it fills higher and higher. And here what I've done is I've created a design alert to tell me that at above 350 psia, highlight those results. And that's how I can very clearly answer our question of when the tank achieves 350 psia. So it's somewhere between 7.5 and 8 seconds. If we need finer resolution than that, that's where we need to reduce the time step. And as a result, we're going to run a few more simulations. So we can do the same thing with pipes as well. So here again, these will all change as we scrub through the simulation and scrub through all the different time steps. And if we go into the transient tab, we can see how the mass flow changes over time. So here, this is the mass flow in pipe 1, which is running from our high pressure, 375 psia, through our valve to our tank. So we see the most mass flow right when it opens, and then it gradually decreases more and more as it approaches that new steady state with the tank completely full. Something else we can do from output is we can create a quick graph. So here we can right click and we can quick graph this parameter. So we'll look at the stagnation pressure in at the tank, and we can see how it gradually increases, and then it's going to asymptotically approach that inlet pressure. As the mass flow rate gets less and less, there's less and less driving force as the pressure in the tank builds. And so it's gradually approaching that 375 psia. If we look at the mass flow, we can look at the mass flow through the valve instead. And we can see that the mass increases significantly right when the valve opens. Again, you're seeing the most mass when the tank is empty and you see the most driving force. And then it gradually decreases and falls off as the tank fills up until it approaches essentially this new steady state condition. So that's how you can use quick graphs from output, but we can also look at these from graph results instead. So when you're doing transient analysis, especially when you're running more than 30 time steps, or you have a much more complex system than this 4-pipe system that we have here, digging through output can be a lot. It can be really useful to determine specific numbers, but generally in transient analysis, you want to look at trends over time. And so to take all this data and visualize it through something like a quick graph is much more valuable than just looking at the numbers themselves directly. So if we go to our graph results tab, here we can have the helper where it'll guide us through the process. I usually close it out and go straight to the transient tab. So the transient tab is going to show us how parameters change over time. It can look at specific junctions or it can look at pipes, and it can also provide more specialized things depending on the type of junction. Here we'll look at general junctions, and we want to investigate the tank. And at first I want to see how the pressure at the inlet changes. So if I have the pressure stagnation inlet in PSIA, I can hit generate. And again, we see that same result from our quick graph. If I hit the crosshairs, I can see how all of these different parameters change over time. So here we can see at 7.5 seconds, we're at 347 PSIA, and then at 8 seconds, we're at 356. So if our criteria is 350 PSIA, and that's the time that we want to determine to fill the tank, it's somewhere in between there, which we could also tell from that output tab. We can also look at the mass flow rate in. So let's see the mass flow rate net at the junction. This is how much mass is accumulating at this tank. Where again, at first we see a massive amount of accumulation because the orifice is creating all that back pressure. Then as it fills more and more and more, we see less and less mass accumulate as it approaches that steady state, where our steady state is going to be the mass in is equal to the mass coming out. We can also add design alerts. So if I add this design alert, here I have one for the tank pressure exceeding 350 PSIA, and we can see how it does so again between 7.5 and 8 seconds. So a lot of different tools that you can use to visualize. Obviously, the more complex your system is and the more complex the transient events are, it's really valuable to take advantage of these tools and visualize the response instead of relying solely on output information. So when we do our analysis, we can take a look at the tank and we can dive into any junction. So if you had valves, control valves, compressors, heat exchangers, even any of the things that we looked at, we can dive into any of those to see how those parameters change over time. Here's a copy of that graph that we were just looking at, where we have the inlet pressure at the top and then the mass flow rate that we're accumulating on the bottom, where we can also add these design alerts to tell us, hey, at what time is it exceeding this 350 PSIA, instead of relying on you, the engineer, to go and determine that manually. So those design alerts, they can identify not only where, but they can also identify when those design conditions are met, or if you have things like minimum pressures that you want to make sure are not drop below during a transient, it can also indicate that to you. We also can remember that we didn't need to specify a transient event within the tank itself. It's instead reacting to the changing system. So as the valve opens, we see that change in driving force, all of that mass is going to flow in. All of those calculations are done automatically for us. We're not saying fill the tank at this pressure rate or at this mass flow rate, anything like that, though we very easily could, right? The next type of analysis I want to look at is a profile animation. And again, all of these different analysis tools apply across all sorts of different transient analysis tools. So what a profile does is it looks at how parameters change across the length of a pipe. Again, if you're familiar with base AFT Arrow or even base AFT Fathom, you should be familiar with plotting those parameters along the flow path. We can do the same thing here, but we can also animate it to show how those parameters are changing over time. So here we can look at the static pressure, and we can also look at the mass flow rate through the system. And we'll also consider the maximum and minimums of those cases. So if we generate, on top we have static pressure, and on bottom we have mass flow rate. And what we can do is we can step through the different time steps. So here we're all fully closed. We can see that our mass flow rate is 0. And then when the valve opens, we see how our flow rate has established itself. And as we gradually fill the tank more and more, we can see how the mass flow rate gradually decreases, again, consistent with the other graphs that we were looking at. So especially if you have interactions, like something in AFT impulse or AFT extreme, where pressure waves can instead transmit along these pipes, profile animations are very valuable in seeing how those interactions occur and how they transmit through your system. So very useful. Again, if you're creating a report and you want to record it as an animation, it makes it very clear. Instead of putting it into words, a picture says 1,000 words, and animation says 24 pictures a second. So you can capture a lot of information in a very quick animation that's very simple to build. So again, profile graphs, any changes along the length of the flow path, any of those same parameters that we were looking at. And it's often fundamental to understanding your system response. So if you get some kind of weird results, usually I would start here, and that will give you some insight into, oh, I didn't anticipate those things interacting, or this valve opened when it should have been closing, things like that. Similarly, you can look at the extreme. So if you're only interested in what max flow rate do I get, or do I drop below a minimum pressure threshold, you can also add that to these graphs as well. Finally, we will peruse what modeling a relief valve looks like, but we won't go through the steps just for time's sake. So there's quite a few different options to build out complex logic within a transient model. And what that lets you do is consider cause and effect during a transient. So if we take a look at our model again, here if we go into this valve, our transient was just changing over time. So the initiation of the transient is at time equals 0.5, the CV should be 1,000. What we can do instead is we can trigger the valve to open. So for example, let's say we had a relief valve and we wanted it to open when this pressure exceeded a certain amount. You could say that the pressure at a pipe is greater than 400 at the inlet of pipe 3. Only if that condition is met should you open the valve. And you can also get more complicated where you can have, if the pressure exceeds this amount and the flow rate is below this amount, then open, or trip your pump, or change this control set point. You can really create a whole range of different options that will all be calculated for you, because once you're starting the transient event, you're really letting the system react to whatever change that you've initiated. You're not specifying every change, you're not specifying every result, you're seeing how these things naturally will interact with one another. So especially if you get more into the software and more into building your own models, again, using this as a resource, and also I believe in the tools menu, multi-condition events, where you can make simple events and then you can create multi-conditions with and or not logic. So much more advanced, far outside the scope of our introduction, but rest assured that it's certainly an option that you have. Again, as I mentioned, there's other options to model a relief valve where we can look at the relief valve considering all of these triggers automatically, where we can have our set pressure. So if that pressure is exceeded, open this relief valve. If it blows down to the certain amount, you can close it. And then we can also say, depending on the pressure that it's seeing, the valve will be open at different amounts. And so there's a lot of flexibility in here that you don't have to build that logic yourself, which is obviously very valuable since engineering time is expensive and everyone wants to get as much work done as they can in as short a period as possible. So here we can open and close based on different criteria. For example, if we were doing a dual event cyclic, we might have a relief valve open if a pressure is exceeded and then close if that blowdown pressure is met. And then you can also consider things like delayed responses. So let's say that you have an automated control system for your relief system and the valve doesn't open for 2 seconds. You can consider that in your transient analysis. The other option is to use the more comprehensive junction models, and that can capture more nuance during a transient. Again, if you're trying to simulate a relief valve, I'd recommend using a relief valve junction instead of trying to build out your own kind of complex multi-event conditions. But sometimes the relief valve might not be able to model it, and you might have to get creative in your modeling. So that's mostly what I wanted to show with AFT Arrow XTS, but we can also kind of capture everything that I mentioned earlier, where there are these different types of transient analysis. How do you know if the event that you're modeling is suitable for Arrow XTS, or you need a different tool like AFT Impulse or AFT xStream? So there's really 2 approaches that we use to model these transient conditions. The first we've talked about in pretty thorough detail, which is the series of steady state snapshots. And the second is the method of characteristics. So the steady state snapshots, as we've mentioned, it assumes a new steady state is reached immediately. In the case of Arrow XTS and also Fathom XTS, there's no heat transfer, and it's not going to capture those acoustic waves or pressure surge. This is again what we call the extended time simulation add-on module, where we're building on the steady state solvers of Fathom and Arrow to capture these transient changes over time. The method of characteristics, the way that we approach it instead is we can cut the pipe into a bunch of different sections, and we can use the relative position of those pipes and other parameters to determine how those things transmit along the pipe. So imagine that this is a pipe, and we can keep track of the pressure and the flow rate and the temperature all along these different sections. And then over time, we can see how if I suddenly increase the pressure here, let's say I did a valve closure and the pressure surged, how does that pressure surge transmit through this gridded out system? So that's how we're able to capture those waves, things that we can't do with steady state snapshots, because again, if we're assuming steady state, we're treating the pipes very differently from how we would using the method of characteristics. So we are able to capture those acoustic waves, and this is where you need a more complex product, something like AFT Impulse or AFT xStream, if you're interested in what we call rapid transients. So those series of steady state snapshots, again, we're considering kind of slow transients, things like tank fillings or very gradual changes. If we want to determine when an overpressure event might occur, but not necessarily model that overpressure event, all of that can be captured in the XTS module, whereas the method of characteristics is suitable for fast transients. So if you have water hammer or surge, a relief event, a sudden change to your pump operation if you need to trip it or if you're starting it up, and then from that, we can also determine the forces that occur on those pipes as well. Across all these things, we're going to see a trade-off between runtime and accuracy. So you can imagine running, steady state is probably simpler for a more complex model, and doing that repeatedly might be easier than segmenting your pipes into a bunch of different sections and doing all those calculations. But regardless of your approach, the input is going to be generally the same kind of four-step approach where you confirm your steady state. What sort of assumptions are you making? What response are you anticipating? And then how do you specify your model? How do you analyze your model? All of that's going to be the same regardless of the solver. So taking a lot of the skills that we've learned here today, you can apply it to AFT xStream, AFT Impulse, AFT Fathom XTS as well. So big question, when should I use AFT xStream instead? Both of these products can model compressible transients, but in the same way that Fathom XTS is going to model that incompressible steady state, and AFT Impulse can model your water hammer events, you're going to see a similar distinction between AFT Arrow XTS and AFT xStream. The first big distinction is heat transfer. So coming up ideally later this month, but we'll see certainly later in 2022 is the release of AFT xStream 2. It will consider things like the thermal capacitance of pipes. So imagine you're piping a super hot fluid. The pipes get really hot because it's touching the really hot fluid. And then when you change it to a cold fluid, the pipes are going to retain some heat and transfer it to the fluid. It will be able to consider that. And then it'll also consider things like convective heat transfer. At the moment, Arrow XTS is limited to adiabatic pipes because, again, tracking that heat transfer implications over time is much more challenging for what we're doing here. And so it's a much more simplified approach, which should be okay for a lot of those long transient cases. xStream will consider things like your peak pressure or really subtle changes to pressure from different waves. So it can consider things like interference. If you have a relief valve open in one case and it drops the pressure, or if one relief valve fails and it slams closes and causes another high pressure wave, that might trigger a different relief valve. Again, it'll try to capture that interaction because we're cutting the pipe into so many different smaller sections. We can see how those pressures and flow rates change throughout the system. Finally, because we can more precisely capture those pressures and flow rates, we can also consider forces. So if you're doing a stress analysis, if you're building a support for a steam blowdown, for example, you might need to look at AFT xStream, run the valve opening, see how the forces change from not only pressure, but the changes in flow rate. And from that, you can export that to your pipe stress analysis tool, whether that be AutoPipe or Caesar, or I'm sure Roar2, I think, also can read those force files. But again, in a lot of cases, anytime you're looking at a rapid transient where you need forces and you need to consider the peak pressure or heat transfer is very significant, that's a case where you need to step up to AFT xStream. Again, it's really using the right tool for the job. So any rapid transient, which hopefully, we've reiterated enough times the distinction between what we would call a slow transient, where it's okay to go immediately steady state to steady state, versus a rapid transient where it can change throughout the pipe itself. So we made it through, we've made it to the summary. Hopefully you guys don't all quit out at the same time, but let's see what we can do to wrap up. So our transient modeling is built upon our existing steady state models in both AFT Arrow and AFT Fathom, and that can answer our common related questions of how long does it take to fill something, what happens when these things are going to be interacting, if I open this valve and this tank blows down, or if I fill this tank, how is that going to transmit through the rest of the system? In general, you're going to take the same approach when doing transient analysis, whether it's a slow transient or a rapid transient. You want to pick an event, specify the transient, have some sort of hypothesis of what you think the results will be, and then we're going to do our analysis to ultimately answer the question that we had at the start. So that's the same across all transient analysis. The tools and the steps are all going to be very similar. So all of our tools have that same event criteria, how you define the transient, how you build out your model with transient duration, things like that. All of that's shared across all of those other applications. So even by learning Arrow XTS, you have a great leg up in learning Fathom XTS or Impulse or xStream. The different approaches to transient modeling have different merits. So steady state snapshots that can easily capture really long transients where things aren't going to be changing super significantly. The method of characteristic instead captures the nuance of rapid transients. So especially if you're checking a peak pressure requirement or a minimum pressure requirement, flow rate supply and ramping of flow rates to a turbine system, for example, that's where you need to use the right tool for the job. So ultimately, it's important to use the right tool for the job. But again, a lot of the skills that you learn for one are going to translate to the others as well. So that's everything that I have for you today. Of course, if you have any other questions, you can always email us at webinars@aft.com. We can always do our best to answer them. If you have any interest in trying out our applications or trying out Arrow XTS on your system, you can also reach out and we will see what we can do to get you set up. If you have any ideas for future webinars, ultimately we do these to create as much value for you, the users or potential users, as we can. So if you run into problems, if you and your team are scratching your head at a problem, feel free to submit a topic and we'd love to consider it for a future webinar. Hopefully this hour has created a lot of value for you. Hopefully you've learned something new. At minimum, hopefully you now know the difference between a slow transient and a rapid transient, or what tool to use in what situation. And hopefully you can take what you've learned today and apply it to your modeling going forward. We hope to see you in another future Applied Flow Technology webinar. Again, we do this all the time. And if you've attended here or if you found it on YouTube, you know where to find us. So thank you again for your time and thank you again for attending. Hopefully it's created some value for you. And we look forward to seeing you in our next Applied Flow Technology webinar. Thanks again.